You for this nice presentation. And yeah, thank you everyone that are attending to this amazing QHack. And it's my first experience into it, and that's actually very cool. So yeah, I decided to title my talk in this way, but then I just realized that everybody was putting, more serious titles. So sorry about that if it annoys you for some reason. So I decided to prepare this talk. So I believe that everybody, even if you have great experience in quantum computing or not, can follow it or most of it. And I also prepared some tutorials that you can check in my GitHub account, and I will share the link right away. So this is the menu of this quantum troll, let's say. So I will start explaining a little bit what is a variational quantum algorithm. Probably you have heard about that before from other speakers, but I will just go to that again. Then the starter is the MetaVQE, which is a recent algorithm that we developed in our group together with Jakob Kotman and with Alan Aspuruguzik. And then the main dish is quantum classifiers, and I will talk in particular about the single qubit classifier, but there are many more, so I will just provide some reference that you can check later on. And then the dessert will be a quantum fitting algorithm that I prepare also these some basic tutorials about how to play with it a little bit from a very general perspective. So as I said, all the receipts are in my GitHub account. There is a tutorial for each of these things, so you can just play with it. You will need to install Tequila. Yesterday there was a talk from my colleague Jakob about Tequila packets. It's very easy to install, or you can just take the code and adapt it to any other backend or penny lane or whatever you prefer. So it's just for you and to enjoy it. So let me start with what is a variational quantum algorithm. As you know, there are many of them, and the variational quantum eigensolver, the QAOA, the quantum classifiers, quantum autoencoder, and basically there is almost a variational quantum algorithm for every possible problem or algorithm for the fault tolerant quantum computation. And the reason is because it's very convenient for the NISQ era. Because we don't need the qubits to be absolutely perfect to obtain some solution of the problem. So we start with some initial state here that I just write down as a phi 0. This could be the first approximation of our state solution, or maybe we have no idea whatsoever about what's the final solution of the problem. So we can start with the 0,0 state, and that's it. Then we have to construct and design a quantum circuit that depend on a series of parameters. These are called the parametrized quantum circuit. And this quantum circuit will transform this initial state into some output state that, of course, will depend on these parameters. And with this state, we can compute the expectation value of some observable. And this observable can be a Hamiltonian, which represents a molecule, or it can be a loss function, for instance, some fidelity or cost function or something like that, that is normally used in quantum machine learning, in variational quantum machine learning. So once we have this expectation value, we can also compute the gradients of this quantum circuit and put everything all together in this minimizer, which is a classical minimizer. So with all the values that we obtain from our quantum circuit, we plug them in this classical minimizer that will recommend a new set of parameters to try. So we close this quantum classical loop, and hopefully at the end we will converge to some particular energy expectation value. This expectation value was typically understood as the ground state energy in the variational quantum eigensolver, but it can be anything. It can be just the minimum of our loss function, and then we can use the parameters that we learn, the optimized parameters, to do something with them and to process them. So this is the general idea of what is a variational quantum algorithm, and there are many, many possible more variants of it. So one of the first problems that we encounter with these variational algorithms is the Barren Plateaus. I believe that there was a talk about that before, so I will only mention what is this. So as you may know, the parameters of this parametrized quantum circuit are initialized at random. The gradients are 0, and the variances of the circuit tend to 0 exponentially with the number of qubits. So we have vanishing gradients, and we cannot minimize the function properly. We get stuck in local minima. This Barren Plateau problem was encountered in 2018 But then there have been a lot of proposals to try to alleviate the problems. For instance, initialize the quantum circuit more wisely, or using local cost functions, correlate parameters, and there are even more proposals. So the idea is we have a Hilbert space, which is enormous. It's exponentially bigger. And if we start at random, it's very easy that we just get lost in the middle of nowhere, and all directions are the same. So it's really difficult to find the proper region of the Hilbert space where the solution is likely to be. And that's why initializing wisely means starting in some point closer to the solution. Or local cost function could also help us to find some map around and find where the solution is going on. But for the purpose of my talk, I would like you to remember that if you correlate parameters, so if you have different parameters in your parameterized quantum circuit and they are related to one with each other, you can alleviate this problem. So this is something that will happen in quantum machine learning and in all these encoding strategies that I will talk about. So let me go back and remind you what is actually a BQE and what is the goal of a BQE. A BQE stands for Variational Quantum Eigensolver, and it was one of the first proposals for variational quantum algorithms. This plot is from the original paper from 2014, so it has been 5 years. So we start with a Hamiltonian that can be written in terms of Pauli strings, which means that we move from a exponentially big matrix of 2 to the power n, where n is the number of qubits, to a set of polynomial terms in terms of these Pauli strings. Let me remind you that these Pauli strings are the outputs of our quantum computer. So we can estimate them efficiently, and that's why it's so useful, this kind of algorithms. So then we have to construct this parameterized quantum circuit that generates the ground state of the Hamiltonian. And to do so in chemistry, we can use what is called the unitary coupled cluster ansatz, which basically decompose this Hamiltonian into small terms. That is T1, T2, T3. And it starts with the Hartree-Fock approximation, which is like the first order approximation to the ground state solution of these chemistry problems. And then unitary couple, the cluster operator, that can be decomposed in terms of quantum gates. So we have a way to construct the ansatz. So the goal is to find, as I said before, the minimal energy of this Hamiltonian with this quantum circuit that we just designed. But this is not the true goal of the BQE, the original true goal. The original true goal of the BQE is not to obtain only one ground state energy. It's to obtain, as a function of some extra parameter in your Hamiltonian, what is the lowest energy. So we have our Hamiltonian is parameterized, for instance, with the atomic separation, and we want to obtain what is the minimum energy in terms of this parameter, not the other points. So the point at atomic separation of 300, for instance, we don't care about this point. We care about the one that is the minimum, because this is related with the activation function of the molecule and with some physical properties that are interesting for us. So the point here is to obtain this minimum here. We need to scan from 0 to 300 in this original proposal. And each blue point is an individual BQE. So you have to prepare the state, you have to optimize the state, computing the gradients, finding these Barren Plateaus, dealing with all the inconveniences. But in the end, we only care about this small region. So the question is, can we avoid to compute these uninteresting points? Can we avoid having to scan over all these parameters, and not only that, but running an individual BQE in each of them? And that was the motivation that we have to introduce the meta-variational quantum eigensolver, the meta-BQE. So we have, as I said, a parameterized Hamiltonian, that this parameter can be the interatomic distance, or it can be the field strength. If we have a spin Hamiltonian, it can be many things. And the goal is to find the quantum circuit that encodes this ground state into the Hamiltonian. So we only have to change this parameter in our quantum circuit, and the rest of the circuit remains the same. So we can use the same solution that we already obtained. So as a comparison, we have the standard BQE that each blue point is the individual minimization. So it's many of them, of course. And the yellow point is the minimum that we are looking for. And then we have the meta-variational quantum eigensolver, which takes some training points, constructs a global cost function with all of them. So you sum all of them together and you minimize the big cost function. And once you have minimized that, you can estimate the rest of points by just running the circuit with the optimized variables and changing the parameter. So this is the circuit of MetaBQE. We have these training points, M of them, and for each training point, we construct a quantum circuit. We encode, we feed the troll. In this case, the troll is the quantum circuit, as you may notice, with these parameters of our Hamiltonian. And we measure, we obtain the expectation value of the Hamiltonian, and then we take another, we change the parameter to another training point, run again, obtain the expectation value, and so on and so forth. We sum all them all together to construct this super big plus function. And that's the thing that we put in our classical minimizer. So in the end, we will have some set of parameters that are common for all circuits, these phi and phi variables. And with them, we have two solutions. We can just run the circuit with the test, this time new parameters of our Hamiltonian, to obtain an estimation of the ground state energy profile. So we don't have to minimize again. We just take the parameters after the big minimization and only change the Hamiltonian parameter, and we obtain this line. Or if the solution is not accurate enough, what we can do is, do again another standard BQE, but this time, instead of initializing parameters at random, we initialize with the result of the MetaBQE. And we call that optimized MetaBQE or opt MetaBQE. And the idea is trying also to avoid these Barren Plateaus somehow. So instead of starting at random, we are not starting at random anymore. We are starting in a region close to the solution, probably, because these optimized parameters will be close to the true solution, the true parameters, if we have run the variational quantum eigensolver individually. So the point is, once we have all this energy profile with the MetaBQE, we can say, oh, here is the minimum. So let's run a more sophisticated minimization, but only in these points, not in the rest of them. So we can save precious computational time. Let me show you only one example. We also try two other examples, but I don't have time for that. So just go to the tutorials where we present all of them, or to the main paper, and you will see the examples with a spin chain and with the simulation of a transmon qubit. So this example is very neat, the H4 molecule with 8 spin orbitals in the STO 3G basis set. And we use this unitary coupled cluster ansatz that I mentioned before with 2 layers. And here we have 2 types of encoding. So as I said before, we have to encode the parameters of our quantum circuit. And how can we do that? So we decided to try a linear encoding, which means that in each rotational gate, we use this linear function, where d is the parameter of our Hamiltonian, the intermolecular distance in this case. Or we can use a nonlinear encoding, which in this case are floating Gaussians. And the reason why we use that is because we know that the ground state of these molecules have these floating Gaussians. So why not helping the optimizer, helping the MetaBQE by providing encodings strategies that are inspiring the physics behind it or in the chemistry behind it. And these are the results. So as you can see, the MetaBQE, it's much better the BQE initialized with the Hartree-Fock approximation, which is BQE 0. And the nonlinear MetaBQE is much better than the standard BQE and the BQE with linear encoding. So clearly, using nonlinear encoding in this particular case is helping. Of course, you need to study which other encodings will work, or what happens when instead of a molecule we have another model like a spin chain and so forth. There are some drawbacks, etc. But the idea is always the same: encoding your parameters into your quantum circuit, feeding the troll with these parameters. Let me check how. Okay, I have 50 minutes. So as I said, there are the code tutorials for this one in particular, but also for the spin chain Hamiltonians in this GitHub account, which is a copy paste of the GitHub repository that we have with the MetaBQE in our group. So you can check both. So let me now change my subject and move to quantum machine learning. So as you know, we have classical neural networks, and then we have quantum neural networks, which can be understood as kernel methods, as Maria showed very recently in an amazing paper, by the way. So let me do this analogy. So we start classical, we have these classical neural networks with input neurons, we have hidden neurons, and then we have output neurons. The hidden neurons are the one that process the data, and with the input, we introduce the data, and then with the output, we we post-process the data, right? And then we have the quantum neural network in a circuit-centric way, which is also an encoding gates, a processing gates, and the measurement gates. But as I said before, we can understand that in the following way. If the processing doesn't contain anything related with the data, it's just a way to change the measurement gates. And the reason why this is useful is because we normally in a quantum computer, we always project in the zeta basis, in the computational basis. So we always measure the state 0 and 1, and that's it. So instead of that, we can just change the measurement strategy and project into another direction. And to do so, we can just plug a bunch of gates before the measurement gate, and that will change the measurement basis. For instance, if we apply Hadamard gate before measuring, we are actually measuring in the x direction. So that's in the end the interpretation of all of these processing and measurement gates. So another question that came out a few years ago with my former group was, what's the minimal quantum neural network? And first of all, what is the most simple but universal classical neural network? And the answer to this question is a single layer neural network. There is the universal approximation theorem that states that as far as you have enough neurons in your hidden layer, even if it's only one, you can approximate any continuous function. Of course, it's not useful in general because you don't want to have 1,000 neurons in a hidden layer. So what we do is we do the deep learning. So we divide this single layer into multiple layers, and the result is similar. But still, you can. There is a mathematical theorem that says that you don't need these extra layers. With one is enough. So what's the most simple but universal quantum neural network? And we just proved that it's just a single qubit. So of course, a single qubit, it can be simulated efficiently with a classical computer. There is no quantum advantage here whatsoever, but it can approximate any continuous function, which is something also important to know. And this is the idea. So the process in a neural network goes in that direction from the input to the output. In our case, our quantum classifier, this input is distributed in all the gates, and these gates are interpreted as hidden layers, as hidden neurons. And we are reuploading all the time the data into this quantum circuit. So how can we encode the data? If we just use a product of quantum gates without anything else, this is insufficient to carry out any non-trivial task because the product of with different unitary gates can be rearranged in another unitary gate. So with a single qubit, if you put rotational y, rotational x, rotational y, and so on and so forth, you can find the Euler angles of it and just compress all the circuit in only 3 gates. So in case, from a point of view of quantum classifier, if we start in this red point and our layer is in the south sphere of this Bloch sphere, we can go there in a very complicated way, or we can just find the proper path that goes more direct to this correct layer. Fine, perfect. But what happens if we change the point? If we have another data point and the correct level will be in another part, but we are using exactly the same gate again. So of course we will end up in the previous point. So it's impossible to learn anything useful from here. So the solution to that is we add some fixed parameter dependency, which will be the data points in the operation. So it becomes flexible and it can be adapted depending on the data point. And this is the idea of data reuploading, which is a kind of feature map. So it's always the same idea. So we have the paths depend on the data, so we can move them around somehow, or at least our circuit can move them around, and we can arrive to the correct solution. This is the intuition behind it, and we also prove it with the universal approximation theorem adapted to this particular single qubit classifier. So as I said, this is a kind of feature map. So there are many other feature maps, and the idea is always the same. We encode the data into a quantum circuit. We have to decide how. We propose the data reuploading strategy. There are other ones. We rotate the state to the current measurement basis using this U gate, and we find the parameters of this measurement gate and also the encoding gate if the encoding gate depends on these parameters. So you can decide to encode the circuit with parameters, and that's it, and fixed operations. Or you can also add some plasticity in this encoding by also providing some variables there. So as I said, the data reloading strategy that we propose has this particular form. So we encode everything with linear functions, which is what we need to prove the universal approximation theorem in this context. And these are the variables that will be optimized with our quantum circuit. So here we don't have any processing layers. Everything is all together processing and encoding. And we always measure in the computational basis because the strategy is to assign different vectors in the block sphere to each class. So we can construct multi-class qubit classifiers by just dividing the block sphere into different sections. And this comes from the Hellstrom measurements, which is the optimal way to project and distinguish density matrices. So this it follows the same idea. And there is also an extension to multiple qubits because of course all this that I mentioned is only for one qubit, but it can be adapted, or you can try to adapt it to multiple qubits, but then you have to think about other things like entanglement or how to design your quantum circuit, etc. So there are many open questions there. And the measurement and cost function in this case is comparing these target states, which corresponds with each class, with the result of your circuit state wave function. So you just compute the fidelity and you minimize the infidelity. So you want to always fit and find the correct target state with the correct data point. We also propose the weighted fidelity cost function, which is just a sophistication of the fidelity cost function, and it's very similar, but it also takes into account the distance with respect to other target states. So in this case, if you have a multi-classification problem, you can improve your cost function. The reason that I show here is just to show you that you can construct a very simple cost function, or you can also try to improve that part of the problem. And this is just one of the examples from three circles problem in this case. So as you can see, with only one layer, it's dividing in three sectors, but like with straight lines almost. But then as you consider more and more layers of this data reloading, it starts to see that there is some circles here. There is this intermediate region here, which is the difficult part to learn. And the accuracy, it's really good. It's 0.9%. 90%. And the random accuracy, if you classify at random and you just assign random target points, is 25%. So it clearly learns what's going on here. And we also run other tests. You can check that in the paper. But we also try to introduce some entanglement with only 2 qubits and also with 4 qubits. And of course, with entanglement, it seems that the accuracy doesn't increase, but you also have to think about how to introduce properly this entanglement, and there is no clear way to do that. So if you want to try it, you're welcome to try it and improve this model. And let me finish with this fitting cost, how to fit a function with a quantum circuit, in particular with 1 qubit. But this comes from the fact that this data reloading strategy and all these encoding strategies work so well because quantum circuits can be written in terms of Fourier series, as it was shown last year. So the point is, if you find the proper way to encode, you can just represent any continuous function because it's decomposed by the quantum circuit as a Fourier series, and a Fourier series can approximate any continuous function. So in the end, the more data reloading you are adding, somehow you can think about it as you are considering more modes of your Fourier series. So that's why you learn all these parameters. So this example that I show here is only for 1 qubit, and the cost function here is just to compute the expectation value of the zeta operator and compare it with the value of the function, which is, of course, rescale to be between -1 and 1. And this example can be shown in the tutorial that I prepared. So you can go there and play with it and try another function, and you will see that it always learns the function. The encoding is also with 1 layer, linear encoding, and that's it. But of course, you can try other encoding and see what happens and see if you can improve it or if you can learn more complicated function with less layers, etc. So with this, let me close with some overview and conclusions. So as I said, and everything that I presented used this correlation between the different layers and the different parameters of your quantum circuit, which is precisely thanks to encoding the data. So each data point is correlating different parts of your circuit because it appears here, it appears there, and it could be a way to avoid this local minima. And then we have we have to design a good feature map. In this case, I call it data encoding. It has other names, of course. And this is crucial for quantum machine learning algorithms, especially for these variational quantum machine learning algorithms, because if you don't encode data properly, of course, you will not be able to learn anything. And that's why all these works in Fourier series and the universal approximation theorem and are so important to understand how we should encode the points into our quantum circuit, how can we estimate maybe the modes of our Fourier series, and so forth. And then one qubit can approximate any continuous function, as I said. The reason is, again, from the Fourier series and the universal approximation theorem. It's super neat to show these results with one qubit, but of course, one qubit is not enough to achieve any quantum advantage. So one should extend these models to multiple qubits. And it also can be used as a multi-class classifier. So you can also think about this as maybe this qubit doesn't have any quantum advantage, but you can plug this qubit in some bigger algorithm that for some reason you need to classify very quick the result of some big calculation, and you can just plug this single qubit there at the very end because it's quantum in the end. And with these encoding strategies, we can adapt them and use them in other variational algorithms, like the case of BQE with the meta-variational quantum eigensolver. And in our case, we reduce the number of optimization and we learn the energy profile of our Hamiltonian in terms of the Hamiltonian parameters, which will be our data points there. And the reason why this is useful is because we don't have to compute all the uninteresting points in our ground state energy and just go and put effort in those that are interesting from us. So some open question is, what about quantum data? So all the time I'm talking about classical data, how to take some data point and plug them inside of our quantum circuit. But of course, we can also use quantum machine learning with quantum data directly. How can we adapt these encoding strategies and all these algorithms to quantum data? And what happens exactly when we have multiple qubits? How can we construct properly the ansatz of our quantum circuit? How can we introduce the entangling gates? Which entangling gates we use? Careful with entangling gates because they can also generate Barren Plateaus. And depending on how do you construct the entanglement, it can be simulated efficiently with a classical computer. So you have to be very careful with entanglement always. And what is the best circuit ansatz, as I said? So with these entangling gates, maybe using control nodes, control phase, because they activate and deactivate entanglement somehow. There are many things to try, and I encourage you to try all these things, and of course to read all the reference that I provided, and there are also in the GitHub repo, and of course I will share this presentation later, because there is a lot of work to do from a heuristics point of view, from a programming point of view, but especially from a theoretical point of view to understand more deeply what's going on with all these quantum machine learning circuits. And with that, I just finished my presentation. Thank you. And don't forget to fill the quantum drawer with your data. That will be very important for the success of your model. So thank you. I'm ready for questions.
Thank you so much, Alba. That was a great talk. I know the title was a bit light, but the content was definitely deep and interesting. I really liked it. I personally really liked your comparison showing the data of using the linear versus nonlinear encodings for VQE. Could you maybe, I mean, you touched on this quite a bit in the talk, but maybe you could sum up like what kind of general considerations go into choosing an encoding for a particular problem?
Yeah, if you don't know anything about the problem or you have no idea how to encode the data, I will recommend that you use this linear encoding because it's the less unbiased one. It's the one that we use also in neural networks. We encode with linear functions because the point is we can prove that with linear function it's enough to achieve universality. But if you have more information about your system and you know, for instance, that the ground state parameters for small systems or because the physics behind it tells you that depend on floating Gaussians, which was the case of this molecule. So why not using that? It's some extra knowledge that you have. And it's the same discussion that you have when you design your parameterized quantum circuit. If you have no idea about how to design it, or you are very constrained because of the hardware, etc., you just use the alternating answers like rotational gates, and then entangling gates, and rotational gates, entangling gates, and so on and so forth. But if you have some knowledge about the problem, which is the case of the unitary coupled cluster for chemistry, you can directly find the correct parameterized quantum circuit, the one that actually encodes the physics behind it. So it's always the same discussion. If you have no idea about how to encode properly, you use the linear function probably, or something that is less not biased, and you know that will achieve universality. Or if you have some knowledge, you are more than welcome to cheat and put more parameters and put as particular functions, etc., because the goal is to obtain a final solution that is correct, and that's it.
Right. Thank you. Yeah, great. Excellent summary. Cool Guy asks, the data re-uploading seems like a unique idea. Was there any analog in classical neural networks?
Actually, what happens with data reuploading is what happens with neural networks all the time. So let me show you this plot here. So in neural networks, we have these input layers that feed the data into each neuron. So we just put the data into the layer, into the neuron here, then the second neuron, the next one, and so on and so forth. With quantum, we cannot do that because we cannot copy data. We cannot just move data from here to there. There is the non-cloning theorem that that doesn't allow you to do that. So you have to do that manually, let's say. But it's exactly the same idea. So each of these hidden neurons contain the data of your input layer. And in our case, each of our quantum gates contain the data of the input, and it's exactly the same analogy. So we just take what's going on classically and reinterpret it from a quantum mechanical point of view, and that's it. So it's nothing new in that direction.
Okay, makes sense. Let's see. Interesting question actually here from Emil Fuster is asking, would you rather have a circuit with 1 qubit and 1 million gates, or a circuit with 1 million qubits and only one layer of 2 local gates?
1 qubit, you can always simulate that efficiently with a classical computer, so it's not any advantage from this side. I mean, it could be a nice theoretical, work, and that's it. But it's not any advantage. On the other side, you have guaranteed that you will find a solution. But to me, it's like a very complicated way to just learn a solution that just use a classical neural network. It's much efficient and easy, and you don't have to call down a fridge and deal with noise and all this stuff. But as I said before, this single qubit, of course, our idea was just to put the simple examples so we can move to more qubits afterwards. But then you can also think about it as a small piece of a bigger algorithm. So maybe in the middle of your super big algorithm with many qubits, you need to classify data, and then depending on the result, do one operation or another. So there you can plug a single qubit, because of course you cannot plug a classical neural network in the middle of your quantum circuit. So it can be understood in this way. But yeah, using 1,000 gates, there is no point, because you can simulate that with your laptop in the end. It's only 1 qubit, so it's a two-dimensional state. So it's just a matter of applying operations over and over. So I will prefer 1,000 qubits, yeah, definitely, especially if they are logical.
Fair question, yes. Back to data re-uploading. So another question, is the data re-uploading strategy equivalent to a classical pre-processing of data plus single upload?
Classical, why? Because we construct the linear function, maybe. So yeah, I mean, there is the classical preprocessing part, if I understand the question correctly, which is constructing the encoding, like the function, like the linear or the floating Gaussians or whatever. And then you use the result of this encoding and you plug them in your quantum computer. So yeah, there is this classical preprocessing part. You can understand it in this way. But at the same time, it's the same as if you encode only the data X, you have also to plug this data classically, let's say. I mean, you have to construct the set of pulses or whatever, that physical operations that encode the data. So yeah, you have to do a small preprocessing first that constructed the linear function and put that in your quantum computer. But now I'm thinking maybe it's also related with the fact that you can also encode data in another different ways. For instance, with the amplitude encoding. And this is directly you perform the operation, and you, with the angles of your gates, it contains the X, the parameters of your data directly. So this is another way to encode. So there are other encoding strategies, and that's why There are different future maps, and the data reuploading is only one way of doing it. So hope that answers the question mostly.
Okay, we'll see. He'll probably be back in the chat if it doesn't.
Okay.
Let's see. So still on encoding. So the postmodern scientist asks, can you comment on the difficulty of encoding your information on the qubit from a hardware perspective? So it seems like for some large data sets, just uploading, measuring, then updating parameters seems like a lot of overhead.
Yeah, and yeah, that definitely it's the case, and that's but not only with this encoding, but also with any variational algorithm. So the problem between the hardware, I mean, the classical and quantum hardware with all these variational algorithms is that you need to connect to different computational paradigms, basically, and they have to talk with each other really fast, because otherwise you just there's a lot of overhead on top of it, etc. So that's something very challenging. In the end here, since we have already a variational algorithm, so we need to talk with a classical computer for sure for the optimization part. Here we are adding an extra overhead. Yes, that's correct, with this data part. But to me, this is not the important overhead here. The important overhead will be to compute all the gradients for all the parameters. So the more parameters you have, the more likely you end up in a Barren plateau, but you have also to compute and all the gradients if you're using a gradient-based method with your quantum computer. And this is a lot of overhead. And that's why the lesser parameters you have, the better. But the idea of these encoding strategies, at least from my point of view, and that was my goal, was to study and see if using this extra pre-processing and classical encoding, let's say, you can save some parameters. So because you are helping the algorithm to encode in a very particular way, you don't need to add so many layers of quantum gates with all these extra parameters that are so difficult to estimate afterwards and provide a huge overhead in terms of computing the gradients, etc.
Cool. Okay. Let's see. I'm going to go to a more general question. I think a lot of people will like to hear the answer to this one. So Amir_E asks, are there any open questions that could be explored for the open hackathon?
Yeah, I mean, that's why I prepared the tutorials and these questions, basically. I mean, these are some of that came to my mind. So, for instance, I'm not sure how to use, how to adapt this problem to the quantum data. So the quantum data means that you don't have access to this classical preprocessing precisely because it's quantum data. So you cannot take it and adapt it wherever you want and put it inside. So you have to think one way to upload the data into your circuit somehow, your quantum one. And a quantum way to do that. So it's not obvious how to do it. And then a good benchmark, like how many, as you have more qubits, try different encoding strategies with different number of parameters. Check different entangling gates, like maybe the layerized entanglement, another type of entanglement, using control phase gates or control node gates for entanglement, etc., and see how many parameters you need to achieve a given accuracy. So then you can compare and see, okay, this encoding is super good for this problem because it requires, 20 parameters, while the linear one requires 50 to achieve the same accuracy. And as I said before, the lesser the parameters, the better, because you have to estimate all the gradients of these parameters, and this is a huge overhead always. And definitely explore other strategies, and not only the linear encoding, of course. Study the Fourier series and see if you can reconstruct some signal. I don't know. There are many things that you can try, and of course more complicated models, 2-dimensional models, 3-dimensional models. How do you encode data in more dimensions? We also provide that in the original paper, but it becomes much more complicated, of course, because you have much more data. You have to define the target state. So yeah, there are many things to try. So I recommend you to check not only the tutorials, but especially all the references.
Awesome. I hope everybody listening is taking notes. Lots of great ideas there for the Open Hackathon. So now that we've got a lot of the fun stuff out of the way, I think we should get serious for a moment and start talking about Star Trek, because I know you like Star Trek. You're a Star Trek fan. So I mean, I know this is maybe not a fair question, but let's go with favorite Star Trek and least favorite Star Trek.
Okay. Did I stop sharing my screen? I would like to.
Yes. Yeah, you're okay.
Okay.
Yeah, would you like to share your screen again? Do you
No,
need to
no,
share
no,
anything?
no, no, no. Precisely, I would like to see your face while we are
Okay.
talking. So,
You're good.
so
Go ahead. Star
no,
Trek.
sorry. Could you repeat? Could you repeat the question? Sorry, I
Oh.
was just worried about closing the window and everything.
No problem. Favorite Star Trek and least favorite Star Trek series.
Series.
Not movie.
Favorite, probably Voyager. So yeah,
Voyager.
yeah,
Okay. Okay.
Voyager. Next Generation is super close, and I really enjoy Discovery. So let's see where Discovery is going, but I really enjoyed. And the worst one to me was Enterprise and Deep Space Nine. Sorry, I know that Deep Space Nine, many people loves it, but I love it at the beginning, but then the final it was very weird in my opinion. So I didn't enjoy it so far.
Okay, you give me lots of answers for favorites and least favorites. That's great. I like that. So, okay, next question. Favorite captain?
Janeway.
Janeway.
Yeah,
Okay.
yeah, I love her. Yeah, Janeway, definitely.
Favorite secondary character?
Data.
Data? What is it about Data that you really like?
I don't know. He's like a kid in a sense that he wants to discover everything. I mean, he doesn't have any bias about anything, and that's super nice. And his fight and to learn how to become human and what makes us human. So it's a lot of philosophy behind it in the end. And yeah, I really like Data. I mean, he has a cat, so yeah, it's perfect for me.
You also have a cat?
No, but I always wanted to have one. Yeah. The problem is I always live in a super small apartments. I didn't want to have a cat in a small apartment. So maybe in the future I can have one.
Okay, that's fair. Have you seen the recent animated Star Trek series, Lower Decks?
No, but I want to. Definitely.
Okay. I would definitely
Yeah.
recommend it. I was very
Yeah.
hesitant at first. I'm also a big Star Trek fan, and I was a little concerned, but I'm also a big comedy fan. And I think they've hit a really good sweet spot of
Oh, good.
it's quite good. I would definitely recommend checking out Lower Decks if you haven't seen it yet.
Yeah,
Lot
it's
of
in my list.
a lot of really good deep cuts in there. A lot of good callbacks to stuff that real fans are going to get. I think you'd enjoy it. Definitely suggest checking it out.
Okay.
So I know you like sci-fi in general. What is it about science fiction that you like? What draws you into science fiction? Is it the technology side? Is it the stories that they're able to address, the sci-fi?
It's a mix of everything. The technology side, I really like it because in the end, I don't know who said this statement, but a famous statement with science fiction is some of big discoveries comes first from science fiction because people imagine what you will do in the future if you have capabilities of building whatever you want. And afterwards, after 50 years, 100 years or whatever, we finally achieve the technology. So it's a kind of goal that it marks in front of you somehow. And then the stories are really cool. So yeah, and the most extreme part of it is, for instance, Black Mirror and all these series, which is taking, I mean, it's science fiction because in some cases, there are things that still doesn't exist, but they feel super close, and all the challenges with ethics and morals that they present are really interesting. And I believe that that's good because we are having this discussion in the fantasy level, but it will also be useful once we achieve that level of technology at some point. So yeah, I really like that thing too.
Yeah, I agree. I think that's a good observation. How sci-fi lets us explore these deep, important questions, but in a way that makes it feel more. I don't even know how to say it. Just more like engaging and more less, maybe not less serious, but less of a chore. Sometimes it's hard engaging with these questions, but sci-fi is maybe a nice fun way to do it. So I don't want to give the impression that all you do is watch sci-fi shows all day.
It takes a lot of time of my time, so yeah, it's more or less correct. So,
but you also do a lot in terms of especially mentoring women and girls in science and technology. I think that's fantastic. I'd love to hear maybe what sort of things you've learned in doing that role that you could tell the rest of us, like what can we be doing more to help encourage women and young girls to get into science and technology.
So for me, one of my personal goals is to go to the first level, which is schools, rather than last levels, which are, people that are still already in the university, and they clearly have an interest in science. Because in the end, in the schools is where it's proved that for some reason, girls in general, not all of them, of course, they have the feeling that maybe it's not for them, and not with all sciences, of course, only with some of the sciences, especially engineering and physics, mathematics. And the point is, if you don't want to be a physicist, it's okay, of course. I mean, you don't like it maybe, and you prefer to do another thing. But it's not because you feel that you are not good for that. It's just because it doesn't interest you, and that's it. And I really enjoy going to the schools and having talks and see not only girls, but also in general, all kind of kids. They feel amazed with science and say, wow, this is super cool. I would like to try that. And I would like to play with that at some point. And I will have a final goal of becoming a scientist in some direction or another. Or maybe not a scientist. Maybe they prefer to do other things, but they have a good impression of science and they enjoy it. And each time that they see something scientific, they enjoy it and embrace it. And in this direction, I'm involved in the GEM mentorship program, which is a Canadian program for taking girls from very difficult backgrounds in some cases and with some economic difficulties to encourage them, but not for doing science in particular, just to provide them tools if they need them, or having someone to talk to that can say, yeah, you're doing great, you just have to continue, go that, yeah, you have to apply to the scholarship, let's do that, let's find your CV, let's see how can we improve it, and so on and so forth. Because sometimes we only need someone that just tell us, yeah, you're doing great, just continue in that direction, and so forth. And I have this kind of people around me at some point, and I believe that's very important, not only for girls, but for everybody.
That's fantastic. Yeah, I really applaud that. I think that's great. And yeah, that point about just encouraging people to seek out what they want to do and do it, and not let other people discourage them. Having that support is really fantastic. That's great. Yeah, that's great to hear. So let's see. Running out of questions from the chat, but I also know that you were put to work at a very young age. I understand. I think I'm being silly the way I'm phrasing it, but you were doing some interesting, very non-science related work as a child. Is that right? Maybe you could share that story with everybody.
Yeah, I mean, nobody believes me each time that I explain that, but my first job, I was 8 years old or so. I don't remember exactly. And I was one of the kids that put the voice in Catalan, which is my mother tongue, of the Teletubbies kids in the bellies,
Yeah, of course. Yeah.
So I just remember, I only have a few memories about that. And one of those, just to let you know how old I am, is I remember that the guy who was in charge of us told us, you shouldn't touch the microphone, it's super expensive, blah, blah, blah. And the price, I will always remember, the price of the microphone was 1 million of pesetas, which was the currency before euro in Spain. So I remember that. I don't know why I have this in my mind, because to me it was traumatic. Like, oh my God, 1 million, that's a lot of money, right? I didn't have idea what was a million at all. But yeah, so there are some episodes of Teletubbies, not all of them, but some of them, that my voice is in the child in their bellies. And I don't remember almost anything. I mean, my parents told me, yeah, it's your voice, can you recognize it? And of course I can't. And I don't know where are these episodes, so I have no idea now where are they. But yeah, I have a past in media. And
how did that come about? How did you end up doing that?
Because the father of one of my friends in a school, he is a professional voice actor. And they were looking for children for these things. So we were all together, like the 20 of my class or even more to the casting. And they just picked some of us to make, I don't know, 5 episodes or so. So not more than that. So yeah, my voice was nice apparently. And that's why I ended up doing this thing.
Well,
then I switched to science later on. So
I'm really glad that it didn't work out and that you ended up instead pursuing science. We're all very grateful for that. Again, thank you so much for being with us, Alba. It was a fantastic talk. Really appreciate you spending the time.
Thanks for the invitation. I really enjoyed it, and yeah, looking forward to see all the projects of QHack next week.
Sounds great. All right, we'll be right back at 11 o'clock with the next speaker. Thanks, everybody.